So you have some more area to deal with, and it looks like on, you know, example 7 here, I'm sort of leaving you to your own devices, like here, look at this, find the area, and you kind of see there are 2 shaded sections. So I'm going to deal with this. I don't even have an equation for the graph that is being described here, but I can fill in the missing pieces here. If I take a look at this and just say, you know what, I'm going to call this one here like region 1, right? And I'll call this one over here region 2. Let's think about those. That really, you do have 2 equations bounding region 1. One of the equations is this one right here, y equals 0. Let's just go ahead and call that. Let's actually use a different color so it stands out, right? This is y equals 0. And then the parabola, which I guess is kind of already in orange, it's a basic parabola. It looks like it's just moved down 1 unit, so that's x squared minus 1. So I have my 2 equations here of what I see being described to me. And when I look at region 1, right, I can use this idea and say, well, do I want to do top minus bottom or right minus left? And I feel like most people think about doing a vertical presentation, which works lovely. There is nothing magical about the location I decide to draw that vertical rectangle. I'm going to handle it as a top minus bottom. I'm going to set up my integral here, and I'm going to say the top function is 0, and the bottom function is x squared minus 1. That's your top minus bottom. Now, limits of integration, of course, are going to come from the x-axis, because I see that little dx there. I'm good. I've got all x values inside my integrands. And so I'm going to kind of imagine, like, well, that rectangle that I drew in there, that vertical rectangle, would start at x equals 0 all the way on the left, and then keep building until I got here, which that intersection point is 1, 0 to 1. So that's region 1. Now, if I set up region 2, okay, so I'm going to add this, right, because I'm just trying to put these 2 separate pieces together. Region 2, okay, well, what do I have? I'm going to draw a rectangle in here. Nothing special about where I draw it, because consistently the top function is always on the parabola, and the bottom function, well, if I move this left and right, is always on the line y equals 0. I need 2 separate integrals because the top and bottom, you can kind of see, is changing from that region 1. Region 1, the top function is y equals 0, and the bottom was the parabola. Here it's switching, so I need another integral, which is no problem. I can do it. The top function is the parabola, and the bottom function is y equals 0. My limits of integration, imagine kind of sliding this thing all the way to the left, would be starting at x equals 1, and then you're building that area all the way until you get to 2. So this is one where, in order to find the area that they shaded for me, I need 2 separate integrals to handle this issue because of the top minus bottom switching places, right? So I can evaluate each one of these and come up with an answer together. So I'll go back to this region 1, and I'll think about, what do I have? I have negative x squared plus 1. And I'll come up with my antiderivative, and I'll throw in the 0 and the 1. But if I plug in 0, everything's gone. So the area of that first region there is 2/3. So this guy in purple has a value of 2/3. Now, if I want to do region 2, which I have highlighted in pink, you kind of see it's a very similar antiderivative, but see how they kind of switched the the signs, right? So same antiderivative, but positive 1/3 x to the third minus x. I'm going to plug in 2 and 1. So then what I'm going to do here, what am I going to do? I'm going to do 8/3 minus 2, and then just kind of move that negative in there. So I have 7/3 minus 1. So it's 7/3 minus 3/3. 7/3 minus 3/3. So that's 4/3. 4/3. So if I add those together, 2/3 plus 4/3, that's going to give me 6/3, which is otherwise known as 2. Okay, so that's your combined area in that region, okay, that I have shaded. Now, if I go to example 8, again, I don't have an image here of what I'm supposed to be doing. I just have to sketch this myself. So when I had the image but no equations, right? No functions. Here I have functions but no image. So you've got to kind of fill in whatever it is that you need to do. So on this one, I'm going to take a look at this and say, okay, let me graph them. And I think this is a line. I can do that pretty easily. That's not too bad. Y equals x plus 1. This one is a parabola. Again, opening down, because I see that negative on the x squared. And I think in order to sketch this, one of the useful tools here is to find x-intercepts. So I'm going to factor out the GCF of a negative, and then factor that resulting trinomial. And that tells me a lot about this parabola. It's a parabola that opens down, and the x-intercepts are at -1 and 3. So I can get a pretty good picture, a pretty good image of what's going on here. So -1 to 3, and it's a parabola that opens down. If I wanted to be even better about it, I'll say, well, the y-intercept is 3. If I put x in 0 in for x, I get 3. So I guess I could plot that if I wanted to. I don't know. Okay, upside down parabola. And I can graph the other one here, which is this y equals x plus 1. So that would be here, and then I'll go up 1, right 1, up 1, right 1. That's pretty well to scale for me. That looks pretty good. And now I have an idea, okay, well, the region between them, let's shade that region. I always think that that's important, to shade what you have going on. And then think, okay, well, I'm going to do vertical, am I going to do horizontal, what makes the most sense? And a vertical presentation, I think, goes really well here. There is nothing special about the place I'm going to put this rectangle. I'm going to put it all the way over here, just for the sake of argument, right? Doesn't matter. You can put it over here on the left. What you have is this is your top function and this is your bottom function. No matter where you slide that vertical rectangle, the top function is always that upside down parabola. The bottom function is always the linear function. So this is consistent, which is awesome. And so I'm going to set it up that way. And again, that's how I want you to think of area. I want you to think about it as top minus bottom dx or right minus left dy, whatever suits your picture, whatever works. So when I take a look at that, your top function is your parabola. Your bottom function is the line. And my limits of integration, well, I can kind of see that they're they are matching up at -1, but I don't know what this one is. My picture is not well enough to scale for me to eyeball that. So I'm going to do what I should be doing here, which is setting these two equations equal to each other to find the intersection points, which will become your limits of integration. So I'm going to move everything over to the left-hand side. And I'm going to factor. So I see that my limits of integration, definitely the -1 is there. I see that. And x equals 2. Okay. -1, 2. So that is my integral that represents the area. But it did say find the area. So I should be crunching up the numbers here and evaluating this. I think it's worth my time to just consolidate these like terms. I don't have another x squared, but you have 2x minus x, so that's x. And then you have 3 minus 1, so that's 2. It's worth it to sort of tone that down a little bit. Now let's go to the antiderivative, which is negative x cubed over 3 plus x squared over 2 plus 2x. And we're just going to go for it. We're going to plug the 2 in. Plug the -1 in. Let's see, -1 cubed would be -1, but the negative is on the outside. Okay, 1/2 minus 2. Okay, so what am I going to do here? A lot of fractions, right? So I'm going to just work my way through 2 plus 4. I'm just going to write 6. And then here I'm going to have minus 1/3 minus 1/2 plus 2. So sometimes what I do is I try to look at those fractions and say, like, oh, do I really need a common denominator? Not really. Negative 8/3 minus 1/3. That's negative 9/3. That's negative 3. And then I have a 6 and a 2. Well, that's an 8. And then I have this little 1/2. So what I have is 5 minus 1/2, which is 4.5. Okay, however you want to write that. 4.5. You want to write 9/2. You want to write 4.5. All of those things look great. Okay, so there's my area. This is the top minus bottom. And this idea of doing area between two curves, you're always going to get a positive answer because area should be positive no matter what. You know, this is a two-dimensional image that has area to it. Even over here, like each one of these, there are positive areas. We're talking about area here. And this idea of doing top minus bottom handles this issue of like that little section below the x-axis. So we had done that earlier in our notes for this lesson. Let me just slide up, try not to get dizzy. Back up here, remember like back with this Calc 1 idea, like, oh, I had to like change the answer to the definite integral to be positive to talk about area. Let's revisit this. If I use this technique, right, I'm going to draw a vertical rectangle in here, and I'm going to say top minus bottom. I'm going to handle this in terms of area between two curves. I'm not going to have any extra part of my work. What I'm going to do is say, oh, I want to find the area of that shaded region. No problem. Let me do top minus bottom, dx. That is going to be what y equals 0 minus the sine of x from pi to 2 pi, because that's what they had shaded. And this kind of handles the negative issue, right? The antiderivative of negative sine is actually positive cosine. So you're going to directly get the answer of 2 without any extra changing on your part. The cosine of 2 pi is 1, the cosine of pi is negative 1, and that gives me a 2. When you're doing area between two curves, top minus bottom or right minus left, you are always going to get a positive answer. Okay, so again, I know this as a definite integral was negative. It's because it's below the x-axis. But if you're being asked a question of area, your answer is always positive. If you have a negative number, something went wrong. Your antiderivative is wrong, or your setup is wrong. Something is wrong. You should always be getting a positive answer to all of these questions about area. That's how it was phrased. Not just, hey, here's a definite integral, come up with a number. Okay, because a definite integral could be negative, but area is always positive. Okay, so let's take a look at the next two examples here, and we'll see where it takes us. So we have to be able to sketch, some of these, generally basic graphs. That this is just y equals x. You've sketched that line a lot. And this is your basic cubic function. So I'm gonna graph them on the same grid. I'm gonna try to make them obnoxiously large. Here's y equals x. It's a straight line. All lines are straight. And then I'm gonna graph the cubic, which looks like this. Sort of exaggerating that a little bit, but that's sort of your basic idea of that cubic. And so I'll label them. Maybe I'll change the color on one of them to make it easier to recognize, right? There's y equals x. So I want the area of the region bounded by these graphs. And if you look and you know about these polynomial functions, right? This line is going to keep going on, and this line keep going down here on the left. They're never going to intersect again, right? You have two regions that you're interested in. It said area, all the area bounded by these two functions. Well, there's two regions here. There's this guy down here, and there's this guy up here. And so you need to come up with the area of each one of those. You could do region 1 and region 2, like we had done before, right? Or not. I'll tell you why not. I mean, these are two odd functions. Those two regions are the same. This is symmetric. You can use symmetry here. So I'll set them up independently, just like we did before, you know, region 1, region 2. But the connotation here is here. If it says find the area, that means all bounded area. And these two graphs create two bounded regions. So that is now your job. Now, when I draw a rectangle in here, right, I'm going to try vertical because that's always nicer, right? And this is consistently, the top function is on the cubic function and the bottom function is on the linear function. If I draw a rectangle in this section, well, the top function is now the linear part and the bottom function is now the cubic part. So this switcheroo issue is why if you're going to do two separate integrals, if you're going to do region 1 and region 2, you can't like smush them together, right? So I'm going to have to do region 1 is going to be the integral. Top function would be the cubic function. Bottom function is the line. When I come over here to region 2, the top function is the line and the bottom function is the cubic function. You see that switcheroo happening here. And I can just put a big plus sign in the middle, like, hey, let me add them together. What I'm missing is the limits of integration. So in order to find the limits of integration, I can see there are intersection points, right? I have to go fishing to find them, which means I'm going to set these two equations equal to each other. And I'm going to do all of my advanced algebra factoring skills. And you can kind of say that these intersection points are really nice. You know, you've got -1, you've got 0, and you've got +1. So on region 1, the limits of integration would be from -1 to 0. On region 2, it would be from 0 to 1. And you could crunch the numbers on each of these. What you can also do, and you'll probably see the textbook do this, is they will use symmetry because these two areas of each one of these regions are the same. This is a symmetric situation. So you could just take one of your integrals and double it. So like I could just say, well, let's just do that and let me just double my final answer. That's possible. You could have doubled that one. There's no reason, right? But you can come up with an answer. And again, you can crunch the numbers on this using symmetry. You can do them separately. You can use symmetry. However you slice it, you should end up with an area of 1/2. Okay, so hopefully that's okay. If not, you can email me and let me know like where you have a mistake somewhere in your work. Okay, but the setup is really important. And symmetry, if you can use it, great. Notice going back to example 7, we could not use symmetry. There is nothing symmetric about those two regions. So just to be clear about that, just because you have two regions doesn't mean you can use symmetry. Here we did not. Okay, but here we did. Okay, so when it's allowable, go for it. All right, so here's our last example in this scenario of area between two curves, which again, this class is a no calculator class. I do need to identify the region, and the region is bounded by 3 equations: this cubed root, a line, and y = 0. So I want to sketch all of those, and I don't have a calculator, so I'm going to sketch what I can. I think I can quickly sketch y = 0 because, well, that's just the x-axis. I'll label it. Let's go ahead and sketch the line, 1 minus x, so the y-intercept is at 1, and slope of -1. And then I have this cubic, cubed root, I should say. Kind of avoiding that one. But I know what a cubed root graph looks like. I also know that the domain here should start at -1. Not the domain, but the x-intercept, should start at -1. And I know what the basic shape of a cubed root function is. I keep saying cubic, I apologize. Cubed root. But plug in 0, I get 1, and it looks like this. Kind of looks like an S. Well, it's sort of a cubic function on its side, for lack of a better word. But there's your cubed root graph. Now I want to shade the region between all 3 of these images. The green line for y = 0, the purple for your cubed root of x + 1, and your linear 1 minus x. So if I come in here and shade, it's this section right in there. And for this one, I think what's consistent for the whole shaded region is drawing in a horizontal rectangle. Let me find a good color to use. This one. If I draw in a horizontal rectangle, this is really consistent, right? Because your right endpoint is on that linear part here. That's my right function. My left function over here is the cubed root function over there. And that's consistent no matter whether I'm drawing it down here or all the way up there. It's consistently right minus left the whole way through. So I'm going to do the integral, the area here, as a right minus left. Now that means my limits of integration are going to be dy. So I definitely know the lower limit is y equals 0, but I don't know where I'm stopping, although you could kind of figure it out because, you know, if x equals 0, y is 1. So I can go ahead and fill that in. And then I'm going to do right minus left. The right function is the function of y equals 1 minus x, which I've got to be careful here. This is dy. This is really important. That's a really powerful thing. That's what told me that the limits of integration come from the y axis. It also tells me that the inside, the meat of my integral, has to be in terms of y. Right now, I have y equals 1 minus x, so that's not good. What I'm going to do is switch this around. I'm going to make this say x equals. I'm going to slide the x over to the left and slide the y over to the right. So there is my expression that I'm going to put in, the right function. Instead of saying y equals 1 minus x, equivalently, I'm going to say, well, x is a function of y. That would be 1 minus y. Same thing over here. I can't just put the cubed root of x plus 1 in here. I have to have x as a function of y, which means I have to get in here with my algebra skills and say, I want to get rid of that cubed root. I'm going to cube both sides. And then again, I'm solving for x. Subtract 1 from both sides. So instead of saying y equals the cubed root of x plus 1, I'm going to say, well, x is a function of y. X is y cubed minus 1 dy. Okay. So I am going to evaluate this definite integral. I'm going to kind of combine some like terms. 1 minus negative 1, that would be 2. And I will find the answer to this. So I'm going to come up with my antiderivative. I am going to throw in a 1 and then throw in a 0, which means, well, everything goes to 0. So 2 minus 1/2 minus 1/4. Let's see. 2 minus 3/4. That would be 8/4 minus 3/4, which is 5/4. Now, you do have options. For some of you here thinking like, well, you know, did I have to do this horizontally? No. There's nothing in the directions that tells you how to do this horizontally or vertically. I'm never going to tell you. You just do something. This is great. I think this is easier. This is one integral. It's one calculation. It's consistent and it's not terrifying. You could do this in a vertical presentation, and I'll just sort of show you that really quickly for those of you that maybe had that idea. Oh, let me undo that. Had that idea, but were unsure of it. You could do that. You could say, hey, on this region, can I draw something vertical? You sure could. Your top function would be that cubed root. Your bottom function would be y equals 0. And so you could do that. But then you'd have to add to that the integral, this other one over here. I have to do a whole nother integral because the top function is now that linear part. And the bottom function is 0. And that would be from 0 to 1. So you could certainly do it in a vertical presentation, right? And so if you crunch the numbers on each of these and then add them together, right, then I should also get 5/4. So if you're curious about that, you could do that. I think it's too much work. I think doing 2 integrals is never as good as getting the answer in 1 integral. So you decide what is consistent. If right minus left gets you through it, then do it right minus left. But you can choose.